The CRP-5 has been designed for commercial aviation students and pilots. If you are undertaking a course in navigation or flight planning, this video will show you the various ways of solving the problems which are posed in commercial aviation examinations. If you are using the standard CRP-5, you will need a pencil and a good eraser of the type shown. We will follow the examples in the CRP-5 handbook, so keep that to hand also. The CRP-5 has two sides. One is the circular slide rule, the other is used for solving the triangular velocities. The circular slide rule incorporates windows and indices for solving navigation and flight planning problems. When setting a problem on it, it is good advice to line up the 10 and the 10 as shown. The red cursor may be used to assist in lining up various numbers. The first example that we will do is one involving ratios. In the above ratio, if P equals 25, Q equals 8 and B equals 9.5, what is the value of A? Orientate the CRP-5 so that the 8 is positioned under the 25, like in the ratio. If you move the cursor to 9.5 on the inner scale, you can read 29.7 on the outer scale. To be honest, the calculation is best approached using an electronic calculator. Although division can be done in a similar way to ratios using the circular slide rule, 462 divided by 17.9 equals 25.8 is best solved using a calculator. The same is true for multiplication. 0.015 multiplied by 0.26 equals 0.0039. Although we recommend that you remember your basic conversions, there are some very nice reminders on the CRP-5. Do try and remember that there are 3.28 feet in 1 metre. However, if you cannot remember, line up the 10 on the inner scale, also shown by the red arrow, with the 10 on the outer scale, and notice kilometres, metres, litres is written in red above it. With the cursor positioned on feet in red on the outer scale, you can read 3.28 on the inner scale. Now to an example. How many feet are there in 4727 metres? Line up 4727 on the inner scale with the metre datum on the outer scale. Then rotate the cursor to the feet datum on the outer scale and read off 15,500 feet on the inner scale. Of course, this type of question may be done using an electronic calculator if you know that 1 metre is equal to 3.28 feet. 4727 metres when multiplied by 3.28 equaling 15,500 feet. Important distance conversions to learn are nautical miles multiplied by 1.15 equals statute miles. Statute miles multiplied by 1.6 equals kilometres, and metres multiplied by 3.28 equals feet. This can be shown on a CRP-5 as follows. Position the 10 from the inner scale under the red nautical mile datum on the outer scale. The cursor is lined up on the red statute mile marker on the outer scale. Underneath can be read 1.15 on the inner scale. Without changing anything, underneath the red kilometre datum may be seen 1.852 kilometres. Let's convert 2650 kilometres to nautical miles and to statute miles. Using a calculator, 2650 divided by 1.6 equals 1656 statute miles. 1656 divided by 1.15 equals 1440 nautical miles. 2650 kilometres may be directly and more accurately converted to nautical miles by dividing by 1.852 to give 1431 nautical miles. Let's convert 363 nautical miles per hour to statute miles per hour and kilometres per hour. Using an electronic calculator, 363 knots multiplied by 1.15 equals 418 statute miles per hour. 418 statute miles per hour multiplied by 1.6 equals 669 kilometres per hour. And more directly and accurately, 363 knots multiplied by 1.852 equals 672 kilometres per hour. Important volume conversions to learn are imperial gallons multiplied by 1.205 equals US gallons, and imperial gallons multiplied by 4.54 equals litres. This can also be shown on the CRP-5 by lining up the 10 on the inner scale with the red imperial gallon datum on the outer scale. Underneath the red US gallon datum on the outer scale may be read 1.2 on the inner scale. Without changing anything, underneath the red kilometres metres litres datum may be read 4.54. Let's convert 25,200 litres to imperial gallons and US gallons. Using an electronic calculator, 25,200 divided by 4.54 equals 5551 imperial gallons. 5551 imperial gallons multiplied by 1.205 equals 6689 US gallons. £2.2 equals 1 kilogram. Let's convert 4290 pounds to kilograms. Using an electronic calculator, 4290 pounds divided by 2.2 equals 1950 kilograms. When we convert between volumes and weights, we must consider specific gravity. Water has a specific gravity of 1.0. 1 litre of water weighs 1 kilogram. Aviation fuels are less dense than water and have specific gravities between 0.72 and 0.82. This means that aviation fuels weigh less than water by fractions of between 0.72 and 0.82. On the CRP-5, line up 1 litre represented by 10 on the inner scale with the red kilometres metres litres datum on the outer scale, and position the red cursor on a fuel specific gravity of 0.74. This now corresponds to 0.74 kilograms on the inner scale. 0.74 specific gravity means the fuel is less dense, therefore weighs less. A reminder, imperial gallons multiplied by 1.205 equals USG, imperial gallons multiplied by 4.54 equals litres. The volume of fuel multiplied by specific gravity equals weight, and kilogram multiplied by 2.2 equals pounds. An example. Convert 708 imperial gallons of fuel with specific gravity of 0.74 into USG, litres, kilograms and pounds. 708 imperial gallons multiplied by 1.205 equals 853 USG. 708 imperial gallons multiplied by 4.54 equals 3214 litres. 3214 litres multiplied by a specific gravity of 0.74 equals 2379 kilograms. And 2379 kilograms multiplied by 2.2 equals 5234 pounds. There is a conversion scale at the bottom of the circular slide rule. Just read from one scale to another to convert temperatures from Celsius to Fahrenheit and vice versa. The formula to convert Celsius to Fahrenheit is Celsius multiplied by 9 divided by 5, then add 32. And the formula to convert Fahrenheit to Celsius is Fahrenheit minus 32, then multiply by 5 and divide by 9. For example, what is 37 degrees Celsius in Fahrenheit? Multiply 37 by 9 and then divide by 5 and then add 32, equaling 98.6. Let's try another. What is minus 40 degrees Fahrenheit in Celsius? Subtract 32 from minus 40, then multiply by 5 and divide by 9, equaling minus 40 degrees Celsius. Speed as a distance measured over 60 minutes can be expressed as a ratio. For example, how many minutes will it take an aircraft to fly 124 nautical miles if its ground speed is 178 knots? This is best approached using an electronic calculator. 178 divided by 60 equals 124 divided by time. Solving for time gives 41.8 minutes. To calculate ground speed, the same equation can be used. For example, if an aircraft covers 138 nautical miles over the ground in 68 minutes, what is its ground speed? Speed divided by 60 equals 138 divided by 68. Solving for speed gives 122 knots. To calculate distance, use the same equation. For example, an aircraft has a ground speed of 354 knots. How many nautical miles will it cover in 94 minutes? 354 divided by 60 equals distance divided by 94. Solving for distance gives 554 nautical miles. Problems involving fuel are solved in a similar way to speed, distance and time problems. For fuel problems, the ratio is fuel consumption or flow divided by 60 equaling fuel available or used divided by time. Let's try an example for fuel consumption. If 5450 kilograms of fuel is consumed in 73 minutes, what is the fuel consumption in kilograms per hour? Substituting into the equation, fuel consumption divided by 60 equals 5450 used divided by 73. Solving for fuel consumption gives 4480 kilograms per hour. Another example, this time for fuel. If fuel consumption is 16.9 imperial gallons per hour, how many imperial gallons will be used in 17 minutes? Substituting into the equation, 16.9 divided by 60 equals fuel used divided by 17 minutes. Solving for fuel used gives 4.8 imperial gallons. Another example, time. If fuel consumption is 510 US gallons per hour and total fuel available is 3,260 USG, calculate the endurance of the aircraft in minutes. Substituting into the equation, 510 divided by 60 equals 3,260 divided by time. Solving for time gives 384 minutes. If you line up the 10 with the 10, an isoatmosphere is created on the CRP-5, and in the airspeed window, a pressure altitude of 0 feet will line up with plus 15 degrees Celsius. It may be seen that rectified airspeed on the inner scale, for example 170 knots, is the same as true airspeed on the outer scale. TAS can also be calculated in the non-ice atmosphere. For example, pressure altitude is 18,000 feet. Correct outside air temperature is minus 30 degrees Celsius. RAS is 170 knots. What is TAS? Using the airspeed window, line up 18,000 feet against minus 30 degrees Celsius. Rectified airspeed is shown on the inner scale marked in red here, and true airspeed is marked in red on the outer scale here. 170 knots RAS on the inner scale is lined up with 220 knots TAS on the outer scale. Let's look at another example. Pressure altitude is 35,000 feet. Correct outside air temperature is minus 47 degrees Celsius. RAS is 280 knots. What is TAS? Using the airspeed window, line up 35,000 feet against minus 47 degrees Celsius. This time using the red cursor, 280 knots RAS on the inner scale lines up with 500 knots on the outer scale. This is an uncorrected TAS. Using the compressibility correction window, TAS of 500 knots divided by 100 equals 5. 5 minus 3 equals 2. 2 what? It is 2 divisions to move the arrow pointing at the compressibility scale to the left. This has the effect of decreasing the initially observed TAS of 500 knots. Now reposition the red cursor through the initial RAS of 280 knots on the inner scale and read off 480 knots corrected TAS on the outer scale. If 10 on the inner scale is lined up with any number between 575 and 675 on the outer scale, an arrow labelled Mach number index appears in the airspeed window. An example best demonstrates its use. If temperature is minus 45 degrees Celsius, Mach number is 0.82, what is TAS and the local speed of sound? Align the Mach number arrow with the correct outside air temperature in the airspeed window. Mach number of 0.82 on the inner scale lines up with a TAS of 482 knots on the outer scale. Opposite the Mach number of 1.0 is the TAS of 588 knots, which is the local speed of sound. Local speed of sound and Mach number calculations may be achieved using an electronic calculator with the following formulae. Local speed of sound is equal to 38.94 multiplied by the square root of temperature in Kelvin, and Mach number equals TAS divided by local speed of sound. For the same example, local speed of sound equals 38.94 multiplied by the square root of 228 Kelvin, which is the minus 45 degrees Celsius plus 273. This results in a local speed of sound equaling 587.98. The Mach number of 0.82 equals TAS divided by 587.98. Solving for TAS gives 482 knots. The temperature rise scale accounts for kinetic heating of the outside air temperature probe. For example, for an indicated temperature of minus 30 degrees Celsius and a pressure altitude of 25,000 feet, RAS of 200 knots, what is true airspeed? Having calculated a TAS of 297 knots, read across the temperature rise scale to find a temperature rise of plus 9 degrees Celsius. This gives a correct indicated temperature of minus 39 degrees Celsius, which can be used to recalculate a TAS of 292 knots. The minutes to hours and minutes scale is coloured yellow and permits conversion from minutes on the inner scale to hours and minutes on the hours scale. 60 minutes is 1 hour. 120 minutes is 2 hours. Try converting 274 minutes to hours and minutes. There is 270 minutes on the minutes scale corresponding to 4 hours and 30 minutes on the yellow scale. Add the extra 4 minutes equaling 4 hours 34 minutes. Line up the 10 and the 10 and a nicer atmosphere will be created on the CRP-5. At 0 feet, mean sea level, the ISA temperature is plus 15 degrees Celsius, and at 20,000 feet it is minus 25 degrees Celsius. If we now look at the indicated altitude on the inner scale and the true altitude on the outer scale at, say for example, 4,000 feet, we find that in the ISA atmosphere they are the same. At 20,000 feet, there is also no difference between indicated and true altitude in the ISA atmosphere. If we lower the temperature at 20,000 feet, the inner scale moves back, true altitude becoming lower versus indicated. If it were warmer, the inner scale moves forward, true altitude becoming higher versus indicated. Density altitude is the altitude at which the prevailing density would be found. If the temperature is warmer than ISA, density altitude will be higher than pressure altitude. If the temperature is colder than ISA, then density altitude will be lower than pressure altitude. For example, airfield elevation is 5,000 feet, surface temperature is +5 degrees Celsius. What is the density altitude? For density altitude, think performance, think airspeed window. Line up the 10 with the 10. At ISA, 0 feet pressure altitude equals 0 feet density altitude. If the elevation of 5,000 feet is lined up with +5 degrees Celsius in the airspeed window, 5,000 appears in the density altitude window. The conditions are still ISA. Let's look at a warmer temperature of +30 degrees Celsius at the same pressure altitude of 5,000 feet. Line up 5,000 with +30 degrees Celsius in the airspeed window. 8,000 appears in the density altitude window. Density altitude may also be calculated using an electronic calculator using the following formula. Density altitude equals pressure altitude plus 120 multiplied by ISA deviation. There are two versions of the CRP-5, the CRP-5 and the CRP-5 wind arm. For the CRP-5 you'll need a pencil and a good eraser of the type shown. We will follow the examples in the CRP-5 handbook, so keep that to hand also. The drift variation fixed scale extends by 50 degrees either side of the true heading index mark. The scale can be used for either applying variation to convert between degrees true and degrees magnetic, or for applying a drift from heading to track. The right hand side indicates starboard drift, the left hand side indicates port drift, and in the centre is indicated true heading. Always remember that you are blown from heading to track. For example, heading is 075 degrees true, drift is 11 degrees port. What is track? The true heading is 075, so line up the inner scale value of 075 underneath the true heading index. Look for 11 degrees port drift on the left hand side of the outer scale, which is here. True track may be read underneath, which is 064. Let's try a slightly different example. This time heading is 227 degrees true and track is 241 degrees true. What is drift? Set up heading 227 degrees true underneath the true heading index. "241 is over here, which is your track. You are blown from heading to track. Drift is 14 degrees starboard. Application of variation is best achieved using the mnemonic "Cadbury's Dairy Milk is very tasty" or "Can Dead Men Vote Twice", which stands for CDMVT. Compass, deviation, magnetic, variation, true. Then draw an arrow going to the left and write down "add it if west". For example, if heading is 217 degrees true and variation is 21 degrees east, what is heading magnetic? East is the opposite of west, so instead of adding for west when you move left across CDMVT, subtract for east. 217 minus 21 equals 196 degrees magnetic. Another example. Heading is 005 degrees magnetic, variation is 8 degrees west. What heading is degrees true? Variation is west. You would add if you were going left across CDMVT, but you were going right, the opposite. Therefore, subtracting 8 from 005 equals 357 degrees true. The slide has two sides. This side depicts the low speed side, marked L at the top right. The low speed arcs marked on it range from 300 to 40. Drift lines radiate outwards vertically. Here is the 10-degree drift line. The bottom section is typically used for calculating headwind and crosswind components for runways. The slide has a graduated scale. On this side it may be used for marking measurements in nautical miles on a 1 in half million chart. The other side of the slide is known as the high speed side, recognised by an H marked at the top right. The high speed arcs marked on it range from 1000 to 150. Drift lines radiate outwards vertically. Here is the 5-degree drift line. Note that the values for speed are presented above the line to which they refer. There is a smaller bottom section for calculating headwind and crosswind components for runways. The scale on this side is for making measurements in nautical miles on a 1 in quarter million chart. The triangle of velocities concerns heading and TAS, wind direction and speed, and track and ground speed. Let's set on a wind velocity of 210 30 knots using the low speed side. Rotate the inner scale so that 210 appears under the true heading index. Position, say, the 130 speed arc underneath the centre dot and count down 30 knots below the centre dot to where the 100 speed arc crosses the centre line and draw across. This shows wind from 210 at 30 knots, drawn down. Let's try an example. Your heading is 116 degrees true, TAS 120 knots, wind velocity 260 40 knots. What is the track true and ground speed? First of all, decide which side to use. Since TAS is 120 knots, use the low speed side. Rotate the inner scale so that 260 appears under the true heading index. Then draw on the wind down. Position TAS of 120 underneath the centre dot. With the wind drawn on, now rotate the inner scale so that the given heading of 116 appears under the true heading index. Under the wind cross, read off 9 degrees port drift and ground speed of 154 knots. Heading is 116. You are blown from heading to track. With 9 degrees of port drift, you are blown 9 degrees port to a track of 107. Let's try another example. Heading is 227 degrees true, TAS 420 knots, track 234 degrees true. Ground speed is 385 knots. What is the wind velocity? First of all, decide which wind side to use. Since TAS is 420 knots, use the high speed wind side. Move the slide to position 420 knots TAS underneath the centre dot. Now put the heading on by rotating the inner scale until 227 is under the true heading index. Track is 234, which is 7 degrees starboard. Draw a line over the 7-degree starboard drift line. Find the given ground speed of 385 knots and draw a line along the 385 speed arc through the 7-degree starboard drift line. Rotate the inner scale until the cross is over the centre line below the centre dot. You may now read the wind direction of 177 degrees true under the true heading index. The wind speed in this case is not easy to count out. To make it easier, move the slide to say 400 knots. This does not affect the reading. 10, 20, 30, 40, 50, 60 knots. (177), 60 knots. Another example. TAS 170 knots, wind velocity 083.35, required track 036 degrees true. What is heading true and ground speed? This is the practical example that you use in everyday flight. TAS is 170 knots, so use the low speed side. Move the slide so that 170 knots appears underneath the central dot. Draw the wind on first by rotating the inner scale so that 083 appears under the true heading index. Count down 35 knots from the central dot. 10, 20, 30, 40, 35, and draw across. Rotate the inner scale to a required track of 036. Drift is 10 degrees port. Now we need to drift balance. Rotate the required track of 036 to 10 degrees port. Check where the wind cross is. It shows 9 degrees port. Rotate the required track of 036 to 9 degrees port. Check the wind cross again. Both readings of drift are the same, 9 degrees in this case, so drift balancing is complete. We can now read our heading of 045 under the true heading index, and a ground speed under the wind cross of 140, 142, 144 knots. Let's check the wind velocity at a turning point using an example. TAS is 220 knots, inbound heading is 195 degrees true, with drift of 6 degrees, starboard. Outbound heading is 278 degrees true, with drift of 4 degrees port. What is the wind velocity? Using the low speed side with 220 knots TAS underneath the central dot, rotate the inner scale so that the inbound heading of 195 appears under the true heading index. Now draw down the 6 degree starboard drift line. Then rotate the inner scale so that the outbound heading of 278 appears under the true heading index. Draw down the 4 degree port drift line. Now rotate the inner scale so that the cross which has been formed is positioned on the centre line below the centre dot. Counting down 10, 20, 30, approximately 32 knots, and wind direction 066 degrees true. Headwind and crosswind components on a runway are solved on the squared section at the bottom of the slide. For example, calculate headwind and crosswind components on runway 19 with a surface wind of 150, 25 knots. First of all, move the slide to position the top line of the squared section through the centre dot. Put the wind on first, which is 150 degrees magnetic, lined up under the true heading index. And count down 25 knots. Move the inner scale so that the runway direction of 190 degrees magnetic is positioned under the true heading index. The cross has now moved out to the right. We have a headwind component counting down of 20 knots and a crosswind component from left to right of about 17 knots. Headwind and crosswind components may be calculated using an electronic calculator using the following formulae. Crosswind component equals sine of the wind angle multiplied by wind speed. The wind angle is 190 minus 150 equaling 40. Sine of 40 multiplied by 25 is 16 knots. Headwind component equals cosine of the wind angle multiplied by wind speed. Cosine of 40 multiplied by 25 is 19 knots. The wind arm is fitted on the CRP-5W. On the low speed side, use the end of the wind arm marked with an L. It has a graduated scale which corresponds to the speed arcs of the slide. For example, this is where we would normally mark a cross for 30 knots. Now if we rotate the wind arm, the 30 knot travels with it on the fixed scale. For example, there is 30 knots lined up with the 10 degree starboard drift line. Let's set on a wind velocity of 210 30 knots using the low speed side. So, don't need a pencil anymore, and I don't need a rubber anymore. All I need to do now is use the wind arm to set on a wind of 210 degrees. Using the low speed side, Check that you are using the low speed end, and there is 30 knots. The inner scale may be rotated, and as long as the wind arm is lined up on where the wind is coming from, the reading will still show 210 30 knots. Let's try an example. Your heading is 116 degrees true, TAS 120 knots, wind velocity 260 40 knots. What is the track true and ground speed? There is 120 knots set underneath the centre dot. Now rotate the inner scale so that the given heading of 116 appears under the true heading index. Now put the wind on, which is coming from 260. Low speed side, low speed end. 40 knots is positioned above 9 degrees port. Heading is 116. You are blown from heading to track. With 9 degrees of port drift, you are blown 9 degrees port to a track of 107. And ground speed is 154 knots. Let's try another example. Heading is 227 degrees true, TAS 420 knots, track 234 degrees true. Ground speed is 385 knots. What is the wind velocity? Put the TAS of 420 knots in the centre using the high speed side. Now put the heading on by rotating the inner scale until 227 is under the true heading index. Track is 234, which is 7 degrees starboard. With a wind arm, you do not need to draw down the 7-degree drift line, but for illustrative purposes, in this example, I will. The 385 speed arc is that one there. You will see that when I turn the wind arm onto the intersection between the 7-degree port drift line and the 385 speed arc, the wind is already shown as 60 knots from a direction of 177 degrees. This is the practical example that you use in everyday flight. TAS is 170 knots, so use the low speed side. Move the slide so that 170 knots appears underneath the central dot. Rotate the inner scale to a required track of 036. Now put the wind on, which is coming from 083. Low speed side, low speed end. Count down 35 knots, which is positioned over 10 degrees port drift. Now we need to drift balance. Rotate the required track of 036 to 10 degrees port. Check to make sure the wind arm has not moved, and check what it reads. It now shows 9 degrees port. Both readings of drift are the same, 9 degrees in this case, so drift balancing is complete. True heading is 045. And ground speed is 140, 144 knots. That's the beauty of a wind arm. Let's check the wind velocity at a turning point using an example. TAS is 220 knots, inbound heading is 195 degrees true, with drift of 6 degrees, starboard. Outbound heading is 278 degrees true, with drift of 4 degrees port. What is the wind velocity? Using the low speed side with 220 knots TAS underneath the central dot, rotate the inner scale so that the inbound heading of 195 appears under the true heading index. Now this is the time when I actually have to draw down on these ones. Draw down the 6 degree starboard drift line. Then rotate the inner scale so that the outbound heading of 278 appears under the true heading index. Draw down the 4 degree port drift line. Now it's low speed side, so turn the wind arm around to see where the low speed end hits the cross. Wind direction from 066. And wind speed of 32 knots. Headwind and crosswind components on a runway are solved on the squared section at the bottom of the slide. For example, calculate headwind and crosswind components on runway 19 with a surface wind of 150, 25 knots. Move the inner scale so that the runway direction of 190 degrees magnetic is positioned under the true heading index. Line up the wind of 150. It's a 25 knot wind, so we have a headwind component of 20 knots and a crosswind component from left to right of about 17 knots. Headwind and crosswind components may be calculated using an electronic calculator using the following formulae. Crosswind component equals sine of the wind angle multiplied by wind speed. The wind angle is 190 minus 150 equaling 40. Sine of 40 multiplied by 25 is 16 knots. Headwind component equals cosine of the wind angle multiplied by wind speed. Cosine of 40 multiplied by 25 is 19 knots.